Alrighty, my friends, this is a real exam problem that came up with real students, real people on a real exam, and it's a limiting reactant and excess reactant problem and percent yield type problem here. And this question is part of a longer series with different questions that I compiled together on limiting reactants. We have a balanced chemical equation as usual, but in this case, we don't have masses of each reagent. We have solutions and we have volumes and molarities. And we're going to do limiting reactant problems with solutions here. So this is a solution-based problem for limiting reactant and yields and whatnot. And we'll do the same things. What is the limiting reactant? What is the concentration of the excess reactant? What is the theoretical yield? And then if the actual yield is this, 0.1530 grams, what is the percent yield? So these questions are common as the color blue in this topic, so to speak. So we'll jump into it, and I'll show you two ways to find out what the limiting reactant is. So I'm going to give a little bit of space here. And this is one of the more common ways that I see students do, and there's nothing wrong with this. Totally fine. What I see is we start with one reactant, say the iron 3 chloride, and we figure out how much of the KOH we need to react with all of this FeCl3. So we'll start off with our FeCl3, and there's 35 mils. I'm just going to convert that to liters. Let me know if you're not sure how I did that, and I can put in the comments or make a video on that. But we have 0.0350 liters of FeCl3. And we want moles because we're doing stoichiometry here because we have a certain amount of one compound and we want to know something about another compound in a balanced chemical equation. So that's stoichiometry, 3 steps. Okay, so first we got to go to moles, and we know that there are, now this capital M, remember it's a hidden unit. It means MOL over liters. It's moles per liter. So every time you see this, you can break it up into this. And since it has 2 units, it's great to convert units. So there are 0.100 moles of FeCl3 for every 1 liter of FeCl3. Now that we're in moles of FeCl3, we can use the mole bridge to get to moles of KOH. So we'll put in this here. Now we want moles of KOH. We want to cancel out moles of FeCl3 based on our balanced equation. For every 3 moles of KOH that react, we need 1 mole of FeCl3. Now for our units, wait a second here. Oh yeah, this cancels with this one right here. Our units are in moles of KOH. And okay, so let's do that. So we have moles of KOH, and we can find out how many moles of KOH we have. 0.035 times 0.1 times 3, 0.0105, 0.0105, and we had 3 sig figs as before. Okay, so that's how many moles of KOH we need. How many moles of KOH do we actually have? Well, there are 25 mils, so 0.0250 liters of KOH, and we'll convert to moles using the molarity here. There's 0.200 moles of KOH for every 1 liter of KOH. So liters of KOH cancel, and if we plug this in, don't really need a calculator, but I'll put it anyways. 0.2, 0.005. So 0.005. Now there's 3 sig figs here and here, so I better make this 3 sig figs. Moles of KOH. All right, so look at this. So the iron 3 chloride needs 0.01 moles of KOH, but we don't have 0.0105 moles of KOH. We don't have this much. We only have 0.005. So we don't have enough KOH to react with all of the iron 3 chloride. Therefore, this is our limiting reactant. This is our LR, and then this one has to be the excess reactant. So that's just another way to find out the limiting reactant. The limiting reactant's the one that produces the least amount of product. And to do that, you could also figure out which one doesn't get used up fully by looking at the reactants. Okay, so now what is the concentration of the excess reactant? So that must be after it reacts, of course. Sometimes they don't say these things, but that's what they are. Whoops, there we are. Okay, all right, so the excess reactant is this one. So we want to know how much of this reacted. Well, we need to know how many moles of FeCl3 reacted with the KOH. So since we know this KOH reacted fully, or we assume we do, theoretically, we'll start off with that. So we have 0.00 mole 500 moles of KOH, and we want to know how many moles of FeCl3 we need. So we use the balanced equation to go from moles of one compound to moles of the other. We want moles of KOH to cancel out. We want moles of FeCl3. And on our balanced equation, for every 1 mole of FeCl3 that reacts, we need 3 moles of KOH. So it's a 1 to 3 ratio. Okay, so we can divide this by 3. Divide by 3. 0.001667. 166. Let's put one more. Oh no, we don't need too many. I'll just do one more than we need. Sig figs. Moles of FeCl3. So this is how many moles reacted in theory if it goes to completion. So how many moles remaining? See, if we want to know the concentration of the excess reactant, we need to know how many moles of there are in our solution. So the moles remaining equals our initial moles, initial moles minus the moles reacted, or reacted moles, I guess, the number of moles that reacted. Okay, so how many moles did we start off with? No idea, but we can figure it out. We have this volume and a concentration, so it would be this first step right here will give us moles of the iron 3 chloride. So 0.0350 liters. And there are, was it 0.1? Yeah, 0.1. 0.100 moles for every 1 liter. I know this is all iron 3 chloride, so I'm not putting the compound here because I'm not changing between compounds. How many moles reacted? This amount reacted. 1667 moles. And when we put this in our calculator, we should get a positive number. You can't have negative moles, right? So 0.035 times 0.1 minus 0.001667. Okay, so that's good. So there's some moles remaining. 0.01833 equals 0.001833 moles remaining. So the concentration is simply, so concentration is moles over liters, moles over volume. We know that there's this many moles, 0.001833 moles. And what's the final volume? We're mixing 35 mils with this mils. Now these are both aqueous solutions, so we can generally just add these two together. If these are different, have different solvents or vastly different concentrations, if they're not that dilute, then you can't just simply add these numbers. But for relatively dilute aqueous solutions, you can just add this up. So 35 plus 25, 35 plus 25. So this is milliliters. And then we got to make it into liters. So for every 1 liter, there's 1,000 milliliters. So basically divide that by 1,000. Okay, alrighty. So 0.001833 divided by, uh, 50, that's just 60, right? 60 divided by 1,000. Okay. 0.03, so 0.0305, 0.03055 moles over liters, which is molarity, capital M, of FeCl3 remaining. Do you see that? I hope that makes sense. Let me know if this isn't making sense to you. Now, we have 1, 2, 3, 4, 1, 2, 3, 4. Oh, actually, look at this. No, there's 3 sig figs. We're good. This is 3 sig figs here. That means 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so this is only significant to here. So we should only report to these 3 digits here. Significant to here. There's 3 sig figs. These are, this should be 3 sig figs, 35.0 minus 25.0. So this has 3 sig figs, 3 sig figs. So this one should have 3 sig figs. So it'll be 0.0306 moles per liter. Cool beans. Okay, great. Radio. So I know these questions are kind of long, but there's not really much way around it. What is the theoretical yield of, oh, we're not making this. FeO. Why did I do Cl3? FeCl3 should be OH3. Of OH3. There we go. Okay, life is good. What's the theoretical yield? Okay, so the theoretical yield is based on the limiting reactant. And when we determine the limiting reactant this way, we're using this method, we don't know what the theoretical yield. But if we determine which one is the limiting reactant the other way, like I first did in part A, the one that produces the least amount of product, then we get the theoretical yield right away. That's why I prefer this method in determining the limiting reactant, because you also get the theoretical yield at the same time. It's kind of like a 2-in-1, but it doesn't really matter, and it doesn't really save too much time, but I do like to do that 2-in-1 the best. So the theoretical yield is based on the limiting reactant, which was KOH. No, yes. And how much KOH do we have? We have 0.00500 moles of KOH. 0.00500 moles of KOH. And we want to find out grams. Okay, well, we got to use the mole bridge. Every time we go from one compound to another in a balanced equation, we need to do the mole bridge. And we want to cancel out moles of KOH. We want moles of Fe. I feel like I did FeCl3 somewhere else too. FeCl3 right here. OH3. And again, everywhere. I think I was stuck on the same question before. Okay, all of these should be OHs. Look, oh no, this is FeCl3. Oh, and this is FeOH3. Right, okay. This is Cl3. I was right there. This is Cl3. Okay. Getting my Cls and my OHs mixed up. Okay, there's a 3 moles of KOH to 1 mole of FeOH, so Fe iron 3 hydroxide ratio. So it's a 1 to 3 ratio. Moles of KOH cancel out. Now we don't care about moles, we care about grams, right? So we got to get to grams. And we got to cancel out moles. Moles of FeOH3. OH3. And we want grams of FeOH3. And for every 1 mole, based on the periodic table, if we add up the molar masses of all the elements, 1 mole weighs 106.87 grams. Okay, we'll plug that in. 0.005 divided by 3 times 106.87. 0.1781. 0.1781 grams of FeOH3. OH3, and we have 3 sig figs, so 0.178 grams. This is how much we can theoretically make. We might not make this much, but on paper, if this limiting reactant was consumed completely and reacted fully, we would produce 0.178 grams of iron 3 hydroxide. Okay, last part of this question, that this is always comes up in some form. If the actual yield is this many grams, what is the percent yield? So we have our wonderful equation, one equation for all three yields, percent yield. Oh, what am I doing? Percent yield equals actual yield over theoretical yield times 100%. That looks better. We want the percent yield. The actual yield is this number here. This, you can't calculate this number. This number is obtained from experiment only. You might calculate it if we get the other two numbers, the other two yields, we can calculate it, but you can't get this based on just theoretical math only. Okay, what's our theoretical yield? It's 0.1781 grams, and multiply that by 100%. Now we're going to do this, and there's something very important afterwards. And some profs care, some profs don't care, but I'll mention this. So 0.1781 times 100%. So 85.9%, 85.9, I'll make that a better 8. 85.9%. Now, it's good practice, even though that this is 3 sig figs, this is 4, our answer should have 3 sig figs, right? But it's good practice to round your percent yields to the nearest whole number, even though we have 3 digits of precision here. And the reason is that the error that we did in the lab, if we were to repeat this experiment, we probably wouldn't be precise to 1 decimal place. I should say, yeah, precise. We probably wouldn't be reproducible to 1 decimal place. So it's, if we were to redo it, we probably wouldn't get like this same number, or a 0.8 or 86.0 or 86.7. Like, it'd be a lot off usually if you repeat the experiment. Usually several percent or even more. It could be off unless you've done this experiment like hundreds of times. You're in grad school, you're doing research. So generally the error that goes on in the lab and repeating the experiment is a lot greater than the precision of your measurements alone. So we often report yields, percent yields, to nearest whole numbers. Okay. Some profs care, some don't, but anyways, there you go.